Hi, welcome. This video will talk about rotational symmetry. Symmetry is basically just something where you do something to a figure and it looks exactly the way it was in the beginning. So if you look at the picture, we have a starting point of, we're looking at a hexagon here, and notice that there's a little yellow dot here. And if we turn it a little bit going clockwise, we end up with this. And when the yellow dot moves to this corner here, we have the hexagon looks exactly the same as the original, except that the yellow dot's in a different place. We can rotate it a second time, moving that yellow dot a little bit further, and yet the figure itself looks exactly the same here as the same here. And then you rotate it 3 times, you can see that the yellow dot has moved, but the overall figure itself, the hexagon, still looks exactly the same as the original. Rotate it 4 times, 5 times, and finally the 6th time you'll notice that it actually came back to the same exact spot. The yellow dot's in the same exact spot, and the hexagon still looks exactly the same. If you're looking for some math words for this, it's called the rotational, rotational order of symmetry of this figure. Rotational order of symmetry. It's kind of a mouthful. What it means, big fancy words, all it means is how many times can you turn it where it will get back to the original exact position. And so for this hexagon, there's 6 sides. If we move it 6 times, we end up exactly with that yellow dot kind of comes back to the same spot. You don't usually get asked that type of a vocabulary question, but sometimes you will. Here's another question on the bottom. What is the smallest fraction of a full turn that you need to rotate the image for it to look the same? So if we know that we rotated it 6 times and it came back to the original position, we know that if we only rotated it once, which was this picture way up here, then that is the minimum fraction of a full turn. So our answer for that would be 1/6. We move it 1/6 of the way around, boom, it's going to land right back on top of itself. And that's kind of it in a nutshell. Let's look at another one. This top figure, the question says, what is the smallest fraction of a full turn? You need to rotate the image for it to look the same. The easiest and most direct way to do it is to say, well, how many congruent pieces do I have? And you can see that you have 1 congruent piece, 2 congruent piece, 3 congruent pieces. So if I move it 3 times, it will end up back on its exact original position. Well, what is the smallest fraction of that? I just want to move it 1/3 of the way. All right, so it's just 1 over whatever number of congruent pieces. This bottom one, what is the smallest fraction? So it's the same question. What is the smallest fraction of a full turn? So again, let's count how many congruent pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 congruent points. So if we rotate it 1/9, it will be the smallest fraction that we can turn where it will land on top of itself again. This top one here, it seems the same. The question is still the same. What is the smallest fraction of a full turn? You need to rotate the image for it to look the same. But notice this one's a little bit different. The thing that's different is we have color here. So we might want to count all of the points going along. But if we look at all these points, they're not all the same. Some of the points are blue and some of the points are white. So we're not going to do that. Where's my eraser? Let's see. So let's get rid of that. We're just going to count, let's say the blue ones, because they're very easy to see. So we'll count the blue points. 1, 2, 3, 4, 5, 6, 7, 8, 9 again. So again, there's 9 blue points. So in order for us to rotate it the smallest fraction, have it land on itself, we're going to move it 1/9. Okay, if we had counted all of the points and we had moved this just here, this would have turned blue, and that's not exactly the same figure that we started with, so that's why we don't count it that way. All right, the one below this, let's see, we have, what is the this one's a little bit different. The smallest number of degrees you need to rotate the image. So it kind of takes what we learned, and it takes it one step further. So we want to count the congruent number of pieces, 1, 2, 3, 4. But what we want to realize now is that we have degrees factored in. So rotating things in one whole circle, we get 360 degrees. So almost every, I think every figure that we rotate 360 degrees lands back on top of itself So that's any figure. But for this one, where it has 4 congruent pieces, the smallest number of degrees, we take 360 and divide it by the number of congruent pieces. 360 divided by 4 will give us 90. So if we rotate this 90 degrees, then it will land right on top of itself. And if you know anything about 90-degree angles, that looks like a 90-degree angle. So that checks out. All right, last two. If you want to try to answer these on your own, hit pause, answer them, and hit play and see if you got them right. Let's see what we have here. The top one, what is the smallest number of degrees you need to rotate the image for it to look the same? So let's count the number of congruent pieces. These points, we have 1, 2, 3, 4, 5 of them. So again, we're going to do the same thing. It's 360 degrees all together in a circle. We're going to divide that by 5. That's going to give me 72 degrees. And then finally, the bottom one, what is the smallest number of degrees you need to rotate it? 1, 2, 3, 4, 5, 6, 7, 8. 360 degrees in one circle. We only need to, split that up into 8 equal sections, and that will turn out to be 45. All right, I hope that this has helped you learn about rotational symmetry.